The channel capacity of a Gaussian channel is a limit for a practical digital communication system. In this video, we will analyze this limit. If we have a Gaussian channel with capacity C, the binary transmission rate in a practical communication system must be below this capacity. RB, the number of bits per second, must be below the capacity. And this capacity is the product between the bandwidth in hertz of the transmitted signal, B, and the logarithm of 1 plus the ratio between the signal power Px and the noise power N0 times B. And in this case, we have assumed that at the receiver, an ideal filter is used to limit the noise power, an ideal filter with bandwidth B hertz. This constraint for the binary transmission rate can be understood in several different ways if we make some definitions. For instance, it is possible to define the signal-to-noise ratio as the ratio between the signal power and the noise power. And this is what we have here inside of the argument of the logarithm. It is also possible to define the spectral efficiency or the binary spectral rate, eta, as the ratio between the binary rate and the bandwidth in hertz. We can define the average or the mean energy per bit as the ratio between the signal power and the binary rate, and it's very common to use the mean energy per bit versus over the N0 ratio, and this ratio can be written as the ratio between the signal-to-noise ratio and the spectral efficiency. Taking into account these definitions, we can rewrite in several different ways the constraint that the capacity is establishing for a Gaussian channel. In this case, a practical communication system must satisfy that the binary rate is below the channel capacity, and the channel capacity can be written as B plus B times the logarithm of 1 plus the signal-to-noise ratio. Now, if we divide on both sides by B, here RB divided by B is the spectral efficiency, and then we can write the expression as the spectral efficiency must be below the logarithm of 1 plus the signal-to-noise ratio. And if we replace the signal-to-noise ratio, taking into account this relationship as a function of the mean energy per bit divided by N0, we can have this alternative expression. The spectral efficiency must be below the logarithm of 1 plus the own spectral efficiency times the mean energy per bit divided by N0. If we get rid of the logarithms, taking 2 to the power the argument, then we can write these expressions. The signal-to-noise ratio must be higher than 2 to the power the spectral efficiency minus 1, or the constraint for the ratio between the mean energy per bit and N0. This ratio must be above 2 to the power the spectral efficiency minus 1 divided by the spectral efficiency. In this expression, limiting the value of EB divided by N0, eta is here in the numerator and here at the denominator. If we compute the limit when eta tends to 0, then the EB to N0 ratio tends to the natural logarithm of argument 2. This is 0.693, or in decibels, this is approximately minus 1.6 decibels. This means that in any practical communication system, the ratio EB divided by N0, mean energy per bit divided by N0, must be above this limit. Looking at this expression, it is possible to plot the spectral efficiency eta as a function of the ratio between the mean energy per bit and N0, in this case in decibels, and to plot over this plane the line that satisfies the equality in this expression. This is the limit for a practical communication system. And practical communication systems are below this blue curve over here, because below the curve defined by this equation. and non-practical systems are above this line. Therefore, this plot can be used to compare systems, because, for instance, if we have a value of 10 decibels for the mean energy per bit divided by n0, and we have for a system that the spectral efficiency is here, another system working in the same EV divided by n0 being closer to the limit is a more efficient system. So we can compare the efficiency using such a representation. We can see that the curve defining the limit between a practical and an unpractical system converges asymptotically to approximately minus 1.6 decibels, as we seen previously theoretically. If we come back to these expressions, here we have a limit for the signal-to-noise ratio. The signal-to-noise ratio must be above 2 to the power the spectral efficiency minus 1. This is a lower bound for the signal-to-noise ratio. Because of this, in some cases, there is a definition for the normalized signal-to-noise ratio as the ratio between the signal-to-noise ratio and this bound. And this means that with the normalized signal-to-noise ratio, the new limit is 1 in linear or equivalently 0 decibels. Therefore, we can understand the channel capacity limit in several different ways.